All right, so fingers crossed. Let's try this. Actually, before I get back into what we've been doing with Maxwell's equations, I'm going to, or with the different equations we did Gauss's law, we did Ampere's law. I'm going to go back to something we learned about last semester, which is relativity. And right now I'm going to call it, though, Galilean relativity because it came from Galileo. It's the relativity that we knew from last semester, right? So a bit of a reminder in here. Because so let's say you got U, and U with respect to the Earth are standing still on the Earth, and so your velocity with respect to the Earth is zero. Should be a vector up there. There we go. You suddenly see my cat Bella moving to the right at a speed of 20 meters per second. So she's flying in the air, moving to the right. And so that's the velocity of Bella with respect to the Earth is 20 meters per second. And then there's also Bella's rival, Lily, is moving to the left at 10 meters per second. So we can say negative 10 meters per second for Lily, and that's the velocity of Lily with respect to the Earth. And then we can also say, let's say that Bella shoots out a light beam. So this is using Galilean relativity, by the way, I want to emphasize. So she shoots out a light beam, and that light beam, so the velocity of the light beam, we'll call it a source. So the velocity of the source with respect to Bella is 30 meters per second. Again, I want to emphasize this is not how we think this works anymore, but just reviewing Galilean relativity for you. So, okay, well, if we were to do the velocity of Bella, right, what's the velocity of the sunbeam with respect to Bella? We would say, or not the sunbeam, sorry, the light beam, the source with respect to Bella, well, she's moving to the right at 20 meters per second with respect to the Earth. The beam is moving, oh, dang it. I just realized I screwed this up. So sorry, this is the velocity of the source with respect to Bella is 30 meters per second. So Bella shoots out a light beam, and she sees it moving to the right at 30 meters per second. And that's the velocity of the sunbeam, I keep saying sunbeam, of the source with respect to Bella. So, yeah, okay. So how would we find out, like, let's say, so we know with respect to Bella is seeing it moving at 30 meters per second. How fast would we see it be going? You might be able to intuitively do this and you say, oh, it's 50 meters per second. So what is the velocity of the source with respect to the Earth? Well, if you remember, we did that neat little trick, the velocity of the source. We could do the velocity of the source with respect to Bella, plus the velocity of Bella with respect to the Earth. And again, that links those two things up. And we can say, well, so that's going to be 30 plus velocity of Bella with respect to the Earth is 20. Boom. And that is 50. So it looks like it's moving at 50 meters per second, right? That's kind of the idea there. Well, what about with respect to Lily? Because Lily is moving to the left at 10 meters per second. How fast does she perceive the beam is going? Well, we can do the velocity of the, so we'll do the velocity of the source with respect to, we're trying to find it with respect to Lily. Well, we know the velocity of the source with respect, let's do again the Earth, plus the velocity of the Earth with respect to Lily, and that'll give us the, because that'll cancel out there, and that'll give us the velocity of the source with respect to Lily. So velocity of the source with respect to the Earth, we just found it, is 50 meters per second. And I'm going to add that to the velocity of the Earth with respect to Lily. Well, we know the velocity of Lily with respect to the Earth is negative 10. That must mean the velocity of the Earth with respect to Lily is positive 10 meters per second. So I can do that. That's going to be 10. So Lily perceives this as moving at 60 meters per second. So she sees it as going super fast, but that's because she's moving, Lily is moving to the left and the beam and everything else is moving to the right. Again, Galilean relativity. Hopefully this is nothing new to you. Okay, now we're going to go back to our equations here right now. So again, we've got Gauss's law. That was that an electric flux, or the integral of a closed shape in some way, is equal to a constant. That's the charge inside divided by epsilon naught. Again, epsilon naught is how easily an electric field moves through empty space or a vacuum. So it's charge inside. We just saw with the last video that Gauss's law for magnets, so the magnetic flux is always equal to 0. So any enclosed shape that you make, the magnetic flux is always equal to 0. And that's essentially because there's no magnetic monopoles. There's always a north pole and a south pole. There's no just north pole or just south pole that exists in nature. And then we also, this was then Ampere's law. We got Ampere's law before, right? And that was the idea you did a path integral. So this is when we have the wire and we found out the magnetic field of a wire or a solenoid. We said the path integral of the magnetic field dotted with the path length that it goes. It's got to be a closed loop in some way. That's what the circle right there means. It's enclosed. Same with these. That's what the circle means. It's enclosed. Okay. All right. So the closed loop integral is equal to mu naught times the current within that closed loop. And so mu naught, that is the permittivity of free space, basically is trying to show you how well a magnetic field moves through empty space. So last big idea was the one that we did on Faraday's law right there. And that's the idea that that a change in magnetic flux over time, so this is the rate of change of magnetic flux, will produce an electric current, or it'll produce an electric field dotted dl, right? So you can see these are similar to Ampere's law over here, although this is equal to a constant here. And this one, it's got the rate of change of flux. And then these are kind of Gauss's laws here. So here, I got it written down there. Gauss's law, Ampere's laws, right there for magnetic and electric field. And basically, the guy we named these equations after, Maxwell, realized, oh, wow, all of these are kind of saying the same thing. So I'm just going to stack them all up and say that they're the same that these will help explain electric and magnetic fields. And then he went, hey, wait a second, we got, this, the electric field dotted with dl is equal to the negative change in magnetic flux over time. And then this, well, I got this, this is the integral of the magnetic field dotted dl, and that's equal to a constant times this current. Well, what if there's also this? What if, so we got a changing magnetic flux produces an electric field. Could a changing electric flux produce a magnetic field? And it turns out that yes, that is correct. So Maxwell modified this equation, so that original equation that I just gave you, and he said, so instead of just this part, boop and boop, he said, oh, well, I'm also going to add in this other term, which is that you got a changing electric flux over time will also produce a magnetic field. So basically, two ways you can produce a magnetic field. One is to just have a moving charge, a moving current. That'll produce a magnetic field. And the other is to have a changing electric flux over time. That will produce a magnetic field as well. Both will produce it. And then what you got out here are constants. These constants here are permittivity of free space, permeability of free space, how well a magnetic or electric field move through empty space. To give you a quick kind of visualization of what that looks like, because I know that these are all just equations. So this will kind of get you. So here's what. So here's kind of ideas. So you got positive charges emit electric fields, negative charges absorb electric fields. So electric fields go in. However, if you got a moving charge, it'll produce a magnetic field. So there's a moving charge and you see the magnetic field that gets produced. So there's a moving positive charge, it gets a magnetic field, and you can even use the right-hand rule to see what direction that magnetic field would go. So basically the idea there, before we go any further, is that charges in and of themselves will produce fields, right? Positive charges, electric field out, negative charges, electric field in. But then the second the charge starts moving, it also produces a magnetic field. Well, and here it's going to continue. Electric fields, changing electric fields can produce magnetic fields. So there's a changing electric field, and it's producing a magnetic field as a result. So here they do it again. Now the changing electric field goes down. It's producing a magnetic field, as you can see there. Hey. So, oh, wait. So electric field changing will produce a magnetic field. So sorry, the other one was a changing magnetic field producing electric field. This is a changing electric field producing a magnetic field. Both kind of the same thing. All right. So, and next up they go, well, if that happens, right, then that means that there must be a chain reaction that keeps taking place. Because if electric fields produce electric fields produce magnetic fields, and the changing magnetic fields produce electric fields, you'll get this propagating wave. Here's a, so in one color, let's see, we're going to go back here really quickly and play it again. So magnetic field, electric field, changing magnetic, electric, magnetic. See if I can do this. Changing magnetic, electric. So you get this propagation of that thing. We call that an electromagnetic wave. So what's another way that this is the guy who makes those really good videos. I highly recommend them. So another way we could visualize this is this little Python script. So basically, if you get basically if you got like a wire or something like that, if you take the charges in that wire and move them up and down, shake them around, accelerate them in some way, they will produce this electromagnetic wave. And here is an example of what they look like. I know they look crazy. So this is actually what we would probably call an antenna. And out of that antenna, you can see, so the vertical ones are electric fields, and then they're also producing the horizontal ones, which are magnetic fields. And it definitely looks trippy, you can see. Yeah, and it's kind of nice. You can visualize this, which these are all in my notes if you wanted to get a sense of what that looks like. Okay, so we'll pause that for now. Let's go back to these equations. So we got all these equations, and with this electromagnetic wave, Maxwell went, and by the way, electromagnetic wave, another thing that we say with electromagnetic waves is that electromagnetic waves are light. It's light. That's all it is. So light is an electric field and magnetic field that are constantly producing each other, and that propagates throughout. So basically, Maxwell not only had this, found this way. He says these equations, well, actually this equation, replace it with that one, will explain light. And that's why so now you can laugh at my funny mug. Punchline. All right. So, yeah. So, okay. So there we go. And then Maxwell went even further. He went, oh, wait a second. This right here looks like a wave equation. A wave equation, which involves differential equations beyond the scope of the course that we just took. So, but I'll give you the kind of rundown with this. Is the wave equation basically it involves a space derivative as well as a time derivative portion. Well, if you have the time derivative portion, the coefficient that's out in front of the time derivative portion, it's similar to what we saw with the second order differential equations, where whatever's in front, that there's significance to the constants that are in front. Whatever's in front of the time derivative portion is equal to the inverse square of the speed of the wave. So what I want you to do is, well, so that's basically this. So take a moment right now, and so this is equal to 1 over mu naught epsilon naught. And so what I would like you to do is to find out what the speed of this wave is going to be. So what the speed of this wave is going to be. So basically, I want you to solve for v. So use this equation, solve for v, and you'll get a number. You'll get a constant, right? Because again, this is a constant, look it up. This is a constant, look it up. If you want to even get really involved, you can cancel out the units and see what the units, because the units you should get are meters per second, right? And figure out what the speed of that wave is going to be. So I'll pause and let you try that. Okay, hopefully you tried that. And what you should have gotten is that, right, the speed is equal to 1 over the square root of mu naught epsilon naught. And if you plug all that in, you'll get pretty much 3 times 10 to the 8, which you may or may not know, that's the speed of light in a vacuum. Yeah, and he got that from electric and magnetic field equations. And you get this. And at this point, people are like, whoa, electric and magnetic fields, really cool. That we can explain all this now. And oh, electromagnetic fields electromagnetic waves are light. Hey, this is awesome. This is really cool. Uh-oh, though, big mistake, right? This doesn't make sense because you got that the speed of light is equal to this constant value. But that can't be true, because what if I'm driving in a car, right, and I turn on my flashlights, right? So the speed of light should be how fast the light is going plus the speed of my car, just like we just saw in the Bella and Lily example, right? So that can't be true. Well, yeah. So the people are like, oh man, we almost got this thing figured out, but hey, hopefully soon we'll figure it out, and you'll be able to do that. But people kept finding solutions to these equations, and finding solutions to these equations, and basically finding that that they were constantly getting these solutions, that we were getting like that the speed of light is equal to a constant. And they're like, what's up? Well, and then it took a while until a guy like Einstein shows up, and he says, I think, and he decided that that Maxwell was right. He decided that our intuition about light and how the universe works is incorrect, that Maxwell's equations are actually correct, and that we need to now rethink the way that we view things like space and time. So in order to do that, he had 2 postulates. So anytime you're going to try something new, you got to go like, oh, here are the new rules that I'm going to come up with, right? And if these are the new rules, then what does the universe look like with that? So the first rule is very similar to what we've seen with Newton's rule. In fact, this is no different than Newton's rules, that the laws of physics are all the same, in all inertial reference frames, right? We did the same thing with Newton. That's nothing new. So basically, if you did any kind of experiment in any inertial reference frame, that means at rest or moving at constant speed, you'll see that momentum is conserved, that F net equals ma, yada, 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 yada. And any kind of physics law will apply. But the second one, and this is kind of the bigger one, is that he said the speed of light is constant in all inertial reference frames. So that means not backlogged Galilean relativity. So again, this is the same image as before. So here's Bella moving at 20 meters per second. Oh, it looks like now I got Lily moving to the left at 20 meters per second. And I got you sitting at rest. That instead of the Galilean relativity idea of, oh, if Bella's moving at 20 meters per second, she sees some light beam move away from her at 30 meters per second that's going 50, that's not the case anymore. It's now everybody, doesn't matter who, if you're Bella, Lily, or you, everybody would see that light beam as moving at the speed of light, 3 times 10 to the 8 meters per second. Doesn't matter how you're going. It's all the same. So Bella, how fast does Bella, who's moving to the right at 20 meters per second, see the light beam go? She sees it as going the speed of light, 3 times 10 to the 8 meters per second. How fast does Lily, moving to the left at 20 meters per second, see it go? She sees it as moving at 3 times 10 to the 8, 20 meters per second. How fast do you see the light beam go? You see the light beam moving at the speed of light, 3 times 10 to the 8 meters per second. Everybody sees the speed of light moving the exact same amount. Okay, so what does that mean then? What has to change? So to get an idea of what has to change, we've got this experiment right here. This is a very common way to set up Einstein's kind of big idea. So essentially, imagine, so here's you again at rest. I'll call you object A. We'll call Bella object B, because she's Bella, so B, there you go. So you are at rest with respect to the Earth, or with respect to object A. So your velocity is 0, and you've got what we're going to call a time clock, a light clock. I'm sorry, a light clock. So it's like a pendulum, except it's a light beam, okay? So you can imagine you got a pulse of light that moves out of a source. Click at t equals 0. The light, the ball of light goes up. We're going to ignore gravity. Gravity's not going to do anything here. So the light beam goes up. It hits a mirror, and then it bounces down and hits a detector. And when it hits the detector, that the time that took to do that, leave the source and hit the detector, that's considered the time it took to do that is delta TA. So that's the amount of time delta TA. And we call this, when it leaves the source, an event. And when it gets hit by the detector, another event. So we say when it leaves the source, that's the event 1. And then when it hits the detector, it's event 2. Kind of like our initial and final moments that we've been doing when trying to solve physics problems. Okay. So now Bella is moving to the right again at a speed v, whatever. She's moving to the right at a speed v. She's got the same light clock that is the same. Oh, it's the same height as ours, so we'll call that height d. So it's the same height as ours. We'll call that height d. And Bella's light clock, so she's moving to the right. And from your perspective, so you're watching Bella, Bella's watching you too, but we're doing this from your perspective. So you're watching Bella, and you see her clock, right? It's moving to the right, so the light beam goes up. It's moving like this. It's going to hit the mirror, and then it's moving like that down, right? And again, that's a distance d. So remember, the speed of light is the same for all observers, both Bella and you. You see it as moving at the speed of light. For shorthand, we tend to just call it c, capital C, or no, I'm sorry, baby c, not so that's the shorthand we'll use for it is c. And then the time it takes for Bella's light to bounce off the mirror and come back is going to be delta TB. And what I would like you to do is find delta TB in terms of delta TA and V. So however fast Bella is going, and then any constants as well. So for example, C is okay to be in there as well. You have everything you know. I'll give you a hint, trigonometry. And so see if you can, trigonometry and kinematic equations. There's no acceleration happening here though. So see if you can figure that out. That's what you're gonna do. Okay. Bye.